clear what it's very.
So what are you talking about? Live?
No, what the way to approach what's that? Oh, meeting recording. So I said,
Yes, yeah.
I don't know if we're being recorded right now, but
Yeah.
what they've done is
Oh, yeah.
they
Oh, yes. Yes. Yes.
I think cannot comment.
Yeah.
Some come to nature.
Ah, I see.
So be aware we'll get to the
Yeah. No.
such forms of
Yeah.
applications.
No, I agree with you. I did a bit of look at the website first. Yeah.
Okay, and so I'll just sit there and
Oh yeah. It's
right. No,
1 minute. Yeah, we have to sit at 1 minute, and then.
no, but when you introduce me.
Okay, so you can stay. It's up to you.
Okay. And then you will.
Yeah, I will give you this, and you will put it in your pocket.
Right. I switch off my mobile as well.
Yeah. And then if for the question you can repeat the question. Just remember to repeat. If not, I will.
Okay. So would the questions be? Would they speak or would they put in the chat?
Oh, they will speak.
Yeah.
So you will have people there and also people in the chat.
No, but those
online they will speak.
They will speak.
Yeah. I will ask them.
Okay, if I miss something.
Yeah.
You help me to.
Are we online now? The microphone is on.
Yeah. Yes, looks good. Yeah, that's absolutely fine.
Okay.
Yeah.
So let's try. I hope people on Zoom can hear me. At least. Yeah. Okay, I think we can start. So good afternoon, everyone. Today it's my real pleasure to introduce Professor Ofer Lahav from University College of London. So Ofer did his PhD at the University of Cambridge, supervised by George F. Statue and Donald Lindenbell. Then he moved to Princeton for a postdoctoral fellow. And then he came back to Cambridge as a senior assistant in research, then an assistant director of research, then lecturer, and then reader in cosmology at the Institute of Astronomy. Then he moved to UCL, to London, as the head of astrophysics in the Physics and Astronomy department. Then he has been the Vice Dean for Research at the Faculty of Mathematical and Physical Sciences at UCL, and is currently the Parent Chair of Astronomy at the Department of Physics and Astronomy at UCL. His main research interests are focused on observational cosmology, and in particular probing and characterizing dark matter and dark energy. And today he's going to talk about AI, shallow and deep learning of the dark universe. Okay, let me try if it works.
Hello, good afternoon. Thanks very much, Nicholas, for the invitation to speak here and for the kind introduction. I have to say it's quite special to have some essence of normality when there are so many upheavals going on in the world. So I'm really grateful that you're sort of keeping the show running. This is, I obviously spent many Thursday afternoons in this room listening to many colloquia, and I know one can choose between taking one topic in depth, especially for the experts, all the great minds, or do something a bit more of an overview. And I've chosen to do the latter and to touch about different issues which bring together cosmology and AI. What a very topical, and I want to take a critical view on this marriage between those two disciplines. So that's what I'm planning to do. The topic shallow and deep, you'll see in a moment what I'm getting at. And I'll try to illustrate that shallow is not so shallow and deep is not so deep. But bear with me. Now, doesn't seem to move.
Maybe if you.
Yeah, I should also say hello to all the people on the line. I mean, it's a challenge to have this hybrid mode. Now, in terms of outline, I thought I'll just give some updates on Galaxy surveys. Some of you are involved in those surveys, but I thought for the broader audience. And then some thoughts about the status of cold dark matter and Lambda, and including the question of when to stop and where to go from here. And then this will be about half the talk, and then I'll move to the AI connection, and I'll do it through examples, mainly with PhD students of mine. In that program, we have CDT, Center for Doctoral Training in Data Intensive Science, which you also have here. And I'll show examples of that and also comment a bit about training the next generation of astronomers in data science. So I'll be covering many different topics, but I think one common theme is this interaction between the AI, the laws of physics, which may exist without us there, and the human knowledge. And some people talk about AI as something which, we'll just give the data to a robot, all the data ever created in astronomy, and they will figure out GR. And others say, let's do it in a way which is more interactive with people, with humans, incorporate the knowledge. So that's the theme. And I would like to use more the term of augmented intelligence than artificial intelligence in this context. So that's the background of that, and all these examples will talk about it. So first, Lambda CDM, well, I'm talking here in front of some of the people who created this model. I think I'm sure you've heard many talks about it here from locals and visitors. So this is the picture. Now, when I was a PhD student here, only 5% was baryonic, but the 95% was cold dark matter, no Lambda, correct? So if you give a talk about Lambda, people would just laugh, right? And then the paradigm has shifted, which is very exciting. I understand George has gave a talk about the paradigm shift, and I heard him giving these nice talks at UCL and in Oxford recently. So you've heard how it will happen. I think I counted 30 years since, in fact, the APM result of this model, which, it's not easy for a model to survive for 30 years. It's something to appreciate. But I think we still don't understand, and I use the word deep here again, what is 95% of it. So that's a big challenge. In any case, very nice, this diagram combining Planck and surveys. You see there is a good story there about power spectrum. And this paper here this is Einstein 1917 proposing Lambda for a different reason. You know the story. This is just a pedagogical slide for maybe people who are a bit remote from this. So every component is defined by an equation of state, W, which is pressure divided by density. For matter, P is 0 for radiation. For matter, W is 0. For radiation, it's a third. And for dark energy, in the form of Lambda, it's -1. W is -1, negative pressure. And then it gives you this straight line of just a constant. And note if W is less than -1, it's very strange, because then the density goes up as the universe expands. So it's not physical, some would say. And another comment is Lambda appears in Einstein's paper 1917 on the left. That's part of the curvature term, while today, at least many physicists would say should be on the right as vacuum energy. Okay, so this is dark energy on one slide. And also to mention that, if we look at the densities, this is the drop of density of matter, and the matter and dark energy were equal to about 3.5 years ago, but acceleration started 6 years ago. And people say, oh, it's a recent event, but it's not so recent. It's 6 years ago. And I believe planetary, the solar system formed somewhere in between, 4.5 years ago. So it's kind of interesting to see it on a time scale. Okay, so a big question is, the community has been busy with, is what is this W, okay? So if it's -1, it's Lambda. What if it's not? What if it slightly deviates from it? And what if it's a function of time? Maybe it's not a constant at all. So these are questions in which community has invested billions of dollars, actually, at least as the target for those projects. How is it done? There are several key probes of this technique, and very famous one, supernovae, standard candles, and the story is well known. In the late 90s, two teams show that the universe is accelerating, and they won the Nobel Prize for it. Similarly, there are standard rulers, both on the CMB and the galaxy distribution. And then there's weak lensing, which seems very prominent, a lot of discussion about that these days, where images get distorted by the intervening matter, and then you learn about growth structure and also about cosmological distances. In addition, you can count clusters by some forms, by X-ray or Sonia-Zeldovich, and so on and so forth, and you would do the so-called mass function. So these have been, well established, very mature. We also know what the problems are, systematics in those probes. And this has led to many, many projects. In my last years here, we were engaged with George and others at 2DF, 2-degree field survey, and then it has led to other projects such as dark energy survey, which is photometric, DESI, which is spectroscopic. I'll say a bit more about those two. And what's coming up, hopefully next year, Rubin-LSST on the ground and Euclid in space, and there are many others. And we played our, little role at UCL with instrumentation for both turning those old telescopes into modern observatories by putting optical correctors, which were both for DESI and DESI, were actually assembled in our basement at UCL by my colleagues Peter Dole and David Brooks. Quite an operation. This is 1 meter across, and you have to polish it and align it to the width of that paper, right? So almost a miracle. It's working so well to see those tiny distortions, especially for weak lensing. And it was also a problem that the ceiling was a bit too low, to put this gigantic camera in each, it weighs several tons, all in our basement in central London. So this is just an idea, and this is just a bit of numbers and connecting it to what's coming later about big data. So I've listed it only a subset, and it's biased towards extragalactic projects, DESI, Rubin, Euclid, SKA, and you can see the amount of data. Obviously, SK is going to be the winner in terms of like 1 petabyte per day, but you can see that even current surveys are coming up. Dark energy survey, 12 million already in the bag. Okay, survey is complete, not the analysis, but it's done. DESI, because spectroscopic, only 35 million, but already 10 million observed. And then billions for those surveys, and also you can see the price goes up. I still maintain that it's about $1 per galaxy. So it's not a bad investment, if you're a stem collector, it's only $1 per galaxy. And also the number of scientists, and there's a whole kind of sociological and anthropological questions on how to manage such large teams. I think there are people in the audience who have some experience with that. So dark energy survey, that's close to my heart, because just months after I moved to UCL, we managed to get involved in that, especially with Fermilab, and then many other institutions, and we have a lot of activity here in the UK, including here the IoA, Richard McMahon has started, especially the quasar element of the survey, which was kind of, if like, additional science beyond the dark energy. But essentially, it combines those 4 techniques I discovered all on one telescope in Chile. It's a $40 million project, relatively modest in price. We got support from STFC and then from DOE. As I said, 3 million galaxies already in the bag, and with PhotoZ and a large subset of them with weak lensing, and thousands of supernovae, compared with hundreds we have now, 400 scientists from 7 countries. and observations finished 2019, already over 200 papers. And if you're interested, we produce a book which tells the story of the survey. I was a bit disappointed with 2DF. There's no record of the story. Who did what? So we thought, let's put the story by the people who have actually created it, but it only includes comments from others, including Martin Rees kindly contributed forward. And we have a chapter on sociology, on philosophy, another one on anthropology of the survey, and so on. So this is kind of the story in a kind of level of Scientific American of how this came about and the results so far, or at least the way they were. So far, the data used in terms of results, they were published in May, and it's for about 50% of the survey, the 3 seasons, and more to come using the full survey of 6 seasons. You may ask, why does it take so long? Well, it's a lot of nitty-gritty details to work out. So this is just a summary of the results. It's quite trendy now to combine data sets. So here it's within the same survey, you can do the clustering as well as the lensing together. And it comes 3 times 2-point functions because we have 2 probes. So you've got 3 combinations of them. You can think of the third as lensing. Lensing, I remember when I remember being here in the early 90s and together with colleagues, especially Anthony Lazenby and Mike Hobson and Sarah Bridle, no, it was difficult to convince people that it's good to combine data sets. And now I find just the opposite. It's difficult to convince people to just tell me, what is it you measure just with your probe? Sometimes it's get washed out when you put more and more and more and more probes. But nevertheless, we are sinners as well. So in this case, just to go to the bottom line, first, I'd like you to perhaps appreciate maybe the number of galaxies is not that impressive, only 11 million, but look, 100 million images, with measured distortion, which then fits into the weak lens, right? So I remind you, again, the intervening matter distorts the images, and you need to measure that per galaxy, the shape. It's very subtle, and there's been lots of work on that, not only in DESI, but also in KIDS and Hyperspeed Prime, and we see more and more in LSST and Euclid. And then you do all these plus, Planck and BO and supernovae, and that's what appears in our abstract, authored by 160 something authors. So it's a party line, alphabetical, and that's the W. Okay, so I told you when it's -1, it's lambda. And I want to draw your attention to this kind of 68% confidence level of about 0.03. Okay, this is one of these plots that you see over and over again. This is omega matter, the density parameter, which when I was a student was believed to be 1, and now it's believed to be about 0.3. That's including the baryons. And the equation of state, -1 is the kind of nice value. And one imagine would be measured when you do all these combinations. And then there's this clumpiness S8, which combines the traditional Jim Peebles sigma 8 with omega m. And there's some dispute there between what Planck finds and what the weak lensing people find, about 2.3 sigma. Now, in such plots, you have to decide when you have green, which is Planck, and black, which is DESI, what do you do? So it's like to combine or not to combine, to be or not to be type of question. What do you do? I should say that one is quite careful because it's a projection of in 2 dimensions of 6 cosmological parameters plus 20-something nuisance parameters. There's a lot to discuss. It's not the topic of this talk, but I want to just draw attention. Nevertheless, when people combine, that's what they get. I'm sure I'll get some questions later on that. Now, just a very brief update on DESI. That's doing really well at spectroscopic. So if you like, it's taking it forward from 2DF and Sloan to measure 35 million galaxies and other, that's also quasars. There's the LRGs and the ELGs and the quasars and so on. And that's despite COVID and other technical problems, it seems to be doing really well. Again, is the UK consortium, which features in there. The lead lab is Lawrence Berkeley. lab. And this is just to say that there are now 10 million spectra. It's the latest update I have from the collaboration and a plot made by a student of mine of, this is only 1.7, but just appreciate that 2DF after 5 years or so had the 250,000. So in terms of industry, there's no question we're doing really well. Whether it would change paradigm, time will tell. So that's a story. There's another problem in this Lambda CDM, which is the Hubble constant. I'm sure you heard a lot about it, but it's 73 from kind of local indicators, Cepheids for supernova, 67 from Planck. And I don't know, I'm sure there's lots of coffee time discussions here about it. I'm sure George has told you his views on that, and maybe others have the opposite view. We were asked to do a review article, which I was pleased to do with a student, Paul Shah, and postdoc, former student here, Pablo Lemos, and we put that, and we put this, traffic light diagram here, which shows the different problems. For example, population size, right? You can have a beautiful method like masers or gravitational waves, but if you have only very few objects, it's difficult to come up with something statistical. But I should say red does not mean that it's nonsense. It means you need more work, okay? But it's a big area, okay? And I don't want to give the illusion that AI will solve it. I think it will need an astrophysical understanding of all these techniques. So the jury is still out. Now, this brings the question when you're facing a situation like this. On one hand, Lambda CDM is doing so well, and at least I showed you one number, 1W, which is minus 1.3 plus minus 0.3. But there is also problems, right, with the Hubble constant and sigma 8. And then it's a question when to stop, okay? Now, some people, when I bring it up, they find it's a bit offending, as if I say, stop doing what you're doing. It's not important anymore. Move on to something else. But actually, it's something, if you look at the literature, it's a big topic, okay? In economics, for example, it's a big topic. You have to decide when do you sell shares and when you buy shares, right? You don't carry on doing the same thing because you'll be out of business. And there's a literature on this quite a lot, including papers by Alan Turing on this, question when you detect the process, when do you say, that's it, I know the answer. So this has kind of bothered me. And I was influenced a bit talking to some economists and others about it, and mainly to Joel Silk, and we end up writing 2 pages, which I discussed with some of you. And I think it's kind of philosophical question, but it's also pragmatic, right? Would you ask a student now to spend 3 years to improve that from 0.03 to 0.01? Right? What's the gain? Well, so I get 2 answers. Again, it could be open to discussion. I talked a bit about it to the students before the seminar today. It could be that could be a viable model, right? When is it that people want to do more is when it's an interesting question. So if there's an amazing model that tells me that it should be minus 0.99 or even a crazy model, I just made it up, minus 0.1, or maybe it's a scalar field and it evolves with time. If there's a target, then it's interesting, right? Then you say, look, if you write a paper, you tell the student you will be rich and famous, you'll come up with something. But it's more tricky when you don't know, but then some physicists, experimentalists say, look, you should keep measuring things because you never know, you might discover something, okay? So there's this approach, and there are similar discussions about what to do at CERN, for example, beyond the Higgs. Would you just refine and refine and refine? And there are different schools of thought, but I think it's good to have the question there. And also to mention in this big picture thing that surveys they've been very beneficial. It's in a way an answer to an article by Simon White from 2007 that, these surveys, yes, they target W, but they discover many other things. So, the Great Attractor by 7 Samurais was done because it came out of a survey, which the purpose was to study elliptical galaxies. To the best of my knowledge, George may correct me, neither 2DF nor Sloan had baryonic acoustic oscillations in their proposal, as far as I know. And they were found, and now they lead to new projects. And in DESI, at least, we did not mention gravitational waves. And then the DESI camera was one of half a dozen or so to see the flash from the binary neutron star. And, we talked about it in this overview paper, more than dark energy. So, I'm saying definitely I don't mean stop the surveys, but maybe refine the questions. So that's the message. Now, with all these billions and billions and billions, what do we do? So it's very easy to sell AI just on the grounds of sheer number, that, you can't ask a student to classify billions of galaxies. You have to do something more automated. But I would also like to bring the other angle that we have to also admit limitations of the human brain. This, I promise you, is not an animation, okay? It's a static question. It's a static picture. You can print it, put it on the wall, and test whether you can see 12 dots simultaneously. If any of you can, please raise the hand either here or in the chat box. So far, I haven't met a human who could see 12 points all at once. So it makes you a bit worried. Okay, maybe it's not a disaster if an astronomer got it wrong and it's not an elliptical galaxy, but an S0 galaxy. But if you go to see your medical doctor to look at your MRI scan and the layout is this, makes you a bit worried. Do they see all the things they should see, right? And so I want to just emphasize we do need some other tools which assist, augment the human brain, however wonderful it is. Yeah.
It's easy.
Right.
You can see the 12.
All at once?
Yeah.
First time. Really, you see all 12? Is this you remember it?
I don't know, maybe I'm integrating.
You're integrated. George is integrated. Well, okay. Well, okay. Well, maybe we'll do some tests later. Okay, great. So there's a whole world now of machine learning. Okay, lots is going on. I put two diagrams there, which I'll elaborate in, of two of the popular algorithms. One is called artificial neural networks, and another is, for example, random forests. And I know there are probably people in the audience, maybe some of them are CDT students and others who probably run morning to evening different algorithms. They're more experienced than me in terms of hands-on, and maybe others who avoid it like a plague. This whole new area, which is not so new as I'll say, but I'm just listing here some of the examples of problems. Classification, that's kind of easy to understand. You want to know what is our galaxy. And when you have huge data sets of billions of objects, you want a machine to do it with some probabilities and so on. Galaxy type, supernova, gravitational waves. Regression, you can do photometric redshift. I'll talk about in a moment. And of course, you can use it for deriving properties of planets and galaxy properties. Inverse problems to do the cosmological parameters in a way which is different, where you don't have to write likelihood, but you just show many simulations. I'll show an example. And it's very important these days to produce what's called generative models. That's where you take a small number of high resolution simulations and teach poor resolution simulations certain properties. And therefore you can produce quite cheaply high resolution simulations. It's quite an interesting area. There are a few examples of that in the literature now. And then there are all these developments, including the deep learning. So let's talk a bit about that, more detail. So first, it's a lot of terminology, many buzzwords, but I would like to think that artificial intelligence is the broader picture. By the way, it was popular to say artificial intelligence in the late 80s, then it became out of fashion, and now it's fashionable again to put AI. It's just names. And then machine learning, I would say, is part of that, and deep learning is part of that, I think. I like this quote, which I remember seeing in The Economist in the 90s when I got interested in it, that only if you know how to make money without machine learning, you can make more money with machine learning. So I still feel like that. It's not that throw away everything else you know. You need your instincts, but maybe you can enhance it. And then, how is it connected to traditional statistics? I gave this similar talk in another forum, and someone was a bit offended that I referred to Bayesian method as traditional. But I think it is pretty traditional, but I remember we had great discussions with people at MRIO who kind of have Steve Gall and others who push that direction. And now probably it's fair to say almost every cosmologist is Bayesian. Not all particle physicists though. But it is traditional. So how do we put it on the framework? Is it just a black box? How do we understand? And there's explainability, interpretability are two topics. How do we minimize biases? Sorry, I see a word was chopped there. But if the training set is not proper, we're trying to classify cats and dogs, but let's say it's 50%, 50% in the sample you wish to classify, but if you had only 1% of dogs, you'll get a biased classification. And this, by the way, does percolate into all sorts of other social problems. And then, should you put physics in or not? Should you just let it data speak for themselves? Should you put some physics in? Should you tell it about energy conservation, for example? But also, how could you learn new physics? So to me, these are the new frontiers. I mean, just to do a mundane thing of classifying stars and galaxies, I have a lot of respect, lots of work there, but I think these are, to me, the heavy questions now. And I think the subject is matured, we should take a view. Coming here, I'm always a bit nostalgic coming to Cambridge, but it brought me memories in the early 90s. And this was the time, the institute was great. You can just work on whatever you want. There was no question of worrying about these grants. Would it go well with STFC? You just work whatever you want. And I was fortunate to get a bit of that with help from the APM. I see Mike is here. We used this modest sample, 814 APM images, and we sent them to 6 gurus. One of them was Vaucouleur, and the other John Hukra, Vandenberg. There was one who refused to do it. I can say now it was Sandage. He refused to do it. He said, classification is not for machines, it's for the art. Rather than classify, and then we got a simple neural network. It was with, you may remember, Michael Story Lombardi, and then I had a talented student, Avi Naim, who programmed it. There wasn't TensorFlow at the time. And we showed that basically you can reproduce classification. And then we repeated it to Manav Banerjee, who was a student at UCL and then a postdoc here. And of course, this whole grown to big industry of Galaxy Zoo, led by Chris Lintott to do it, using citizen science. But I have to say, it was kind of fun to do it in those days, away from the crowd. It's infringes, people couldn't tell why we're doing it, but it was fun. That's the advantage. I was talking to the students. Sometimes you walk a bit off the crowd. At least you can do it in peace and quiet for a while. So things have changed a lot. Later, people talked about this problem of photometric redshifts. It's quite a simple problem that essentially you see a spectrum of a galaxy, say different redshifts, but you only observe it photometrically, say through 4 or 5 bands. So it's an inverse problem, which naively I thought could be solved very quickly. So we use this neural network, you feed 5 magnitudes, different colors, and you get a redshift. That's if you like the neural, if you think of it, machine learning, if you want to just think of it as a nonlinear function of the magnitudes. Okay, now there are dozen or so methods like this. And this is, I'd like to think photometric redshift is like an absolute nuisance for the cosmologists. It's absolutely boring. And if you could just measure spectra, that's it. That's what we're doing DESI. But for machine learners, it's wonderful. It's an absolute delight. You can play with different algorithms and do different things. So they like that, right? So lots of activity there. And I mentioned neural networks. There's this method. Again, the CDT students get a whole course, I'm sure the same here, of machine learning. But this is just to give you a bit of a sense of what's going on here. For example, decision trees that you can use decisions based on parameters, and you can randomize it. You can have a subset of the data, subset of the parameters, and then you can do like an average. You take a vote of the different decision trees. That's why it's called a forest. So this is just 30 seconds on that algorithm, which is easy to use these days. Now, what has happened? You may ask, what happened? Okay, people have worked on it. And you can see a plot here, a bit difficult to see, but it's just papers with deep learning in their title or abstract against year. And you see that's more or less, we played a bit with it in the early 90s, for example. And then it was very plateau and suddenly it jumped. So something happened, and this something is the so-called deep learning. So let me explain that. And again, I'm sure there are practitioners here, so forgive me for the shallow explanation of deep learning. So what it is in the standard way, the way we've done it, is to take an object and extract features, okay? So you extract a dozen or so parameters in advance, and you use your knowledge as an astronomer. There's a bulge and a disk, right, for example. So you put it in, you measure bulge to disk ratio, for example, will be one of the parameters. You feed those, and then there's these hidden layers, which nobody can really understand well, and you get the output, and it tells you if it's a car or not a car, for example. In deep learning, what you do, you show the whole image. You don't do any pre-analysis of the image. Now, this is really, you can see what it has done. This is just in the astronomy literature, okay? I looked at just specifically deep learning. This is broader on machine learning. Just deep learning, I checked it, if I counted correctly, it went from 20-something in 2017 to 80, 90 past year. So every 4 days, someone writes a paper with deep learning in the title. Okay, and it will continue until people get a bit bored with it. And then you put something else, right? That's usual. But it's just amazing. It's really cool. So people find it wonderful. You just put something, I would say you don't have to think anymore. So I'm actually taking a critical view, although many of my students write deep learning, I'll share results, and it does good things. And computer scientists who look more deeply into it and translate it to Bayesian methods, etc., tell me that it's still not entirely clear why it does so well. But the point is, I still think that there's something to be said for the shallow learning, that actually you put some knowledge into the system rather than just showing the full image. Just to elaborate a little bit, what's the trick? What's the trick that you show the whole image? The trick is that you actually this pre-processing is built in, and you convolve the image with filters. Now it's another question, how do you choose these filters? But there's some guidelines. So you choose it, you choose all these different filters, you convolve, so you produce many versions of the image. So if you like, it's replacing what you do when you a priori extract bulge to disk ratio. It will have to find it. And if it doesn't know whether it's a bird or a galaxy, it will just try different filters. And then it will tell you whether it's a bird or a sunset or a dog. So that's what it is. Now, people have pushed it. I showed the photo Z. So this is a nice paper by a French group that they actually said, instead of now measuring 5 magnitudes within a particular radius, which is a bit ad hoc, why don't we actually show the whole image, say in 5 filters? And it seems to work well. It's this diagram probably doesn't do great justice, but there's some numbers there about the delta Z. So this is using this full image, and that's just using the standard way of using filters. Sorry, just magnitudes. And okay, the image is not doing a great job, but I think they do show that there is an improvement. And you can say, well, if we put so much work into surveys, why not doing the best? So I'm happy with that. With a student of mine who recently defended his thesis, Ben Hedges, we went again into that problem, and using 1 million Sloan galaxies, what Ben has tried is to do just the magnitudes, but also to use the full images, okay? So this is contrasting the two. Again, it's difficult with the scatter diagram, but if you look at numbers, the mean square error is improved by a factor of 2 if you show the full image. He's taken another step of combining both the full image and some magnitudes. One is to do it with care because you do a bit of double counting, there's correlation. But I think it's quite, I think it has its place. So I'm not preaching not to do deep learning. I'm saying do it, but also do the standard one and maybe look in ways to combining them and put some knowledge into it. And just think about even just the size of the galaxy already tells you some of the distance, right? So it's not surprising that it's doing better. And one can take another step That's with another CET student, Sunil, and former postdoc Will, and former student Antonella Palmassi, Will Hartley. You can also use all this to actually, for those interested in galaxy formation and so on, to do the stellar mass. So it's a two-dimensional plot, stellar mass and redshift. And this is just when the training set is better, is deeper, you get much better constraints. And finally, also in this thing about images, this is another CDT project with a student called Prab Pambra and my colleague Benjamin Joachimi. So this comes now to explainability. Okay, so could we tell what is it in the image that tells us that it's a bar galaxy? So what has happened here? We use the galaxy zoo sample. So many observers, right, looked at it and said, we see a bar, or we see a bulge, or we see a disk. And then we used a technique which was invented by others, not by us, called smooth grad. And what it is, it's basically the derivative of the output with respect to the input. So you bypass all the mess about those hidden layers, too complicated. You just look at the response, and you can get a heat map, or some call it saliency map. So this is the image. Again, the projector doesn't do great justice to it, but it's the image. And it does show, this is the heat map. It does show that indeed there is something which looks like a bar there, or a bulge, or spiral. So we like to think it's a step in explainability. Not only that, you can now turn it into a machine that measures size of bars. And that's a plot of a bar measured by this technique compared with visual one by Hoyle. It's not Fred Hoyle, but Ben Hoyle, who measured it on actual images, okay? So this is also quite exciting. Now you can, switching from galaxies, individual galaxies, to the big picture. In fact, you can think about this with almost any reconstruction method. Now, I've mentioned to you the activity in DESI and also in other surveys of weak lensing, where you basically measure the distortion of galaxies, and with DESI we have 100 million with shaped measurements. And then we thought, could we get a good mass map? Now, this is an old history, and Nick Kaiser, who worked here for many years as well, and Squires came up with a method, I think 93. It's quite no, also 30 years. And they produced that map, I think that one. This is actually applied to DES, and that's to simulations. And then there's Wiener filter, which many of us use for other problems in large-scale structure. And here is another method, which devised by my former student, Maya Jeffrey, to call deep mass. Of course, everything deep sounds good. And that's a particular method called UNet. And so what you do, just I want to get the concept, all you have to do there is just to solve that simple equation. I put here at the top, that gamma, the shear, is just some matrix times kappa plus n. And kappa is the projected mass. What you have is gamma, you're trying to get kappa, okay? You're trying to get a projected mass between you and the sources. So it's an inverse problem, basically. And Kaiser and Squires came up with an elegant solution. But for example, it doesn't take into account noise. So what has been done with deep mass is to actually produce, 3.6 million, 10 to the 5 simulations, right? Hundreds of thousands of simulations. And you essentially teach this algorithm the mapping between one to another. Now, the merit of that is that you can do things in what we would like to call forward modeling. You take the simulations and you degrade them to look as bad as the data in terms of resolution, shape, noise, and all that. So the machine learns the whole story. Okay, that's the concept. Lots of details. You're welcome to look at the papers, but it seems to do a good job. Some numbers there, 11% improvement. I mean, we looked object by object. It's not as if you discover something completely different, but you improve things, right? And then this has led to this map of using the year 3 that I mentioned to you from DES, 100 million galaxies with shape measurements. And using a combination of techniques, traditional and machine learning, this is the map, which is over 5,000 square degrees. This is a zoom in. Bright spots are overdensities, clusters, superclusters, and black are voids. This is just the Milky Way from Gaia, and the LMC, SMC just for orientation. And this picture obviously was picked up. The BBC liked it, both online and television. So this happened in May when we released it. And but of course, the ultimate judgment is what does private eye say about it. And you cannot read, but it says this is our most comprehensive dark matter map yet. This one. So, you know, this is the ultimate publicity you get. Right. So then you can also do reality test and look at this map, and on the sky, look at the Campo map, and as a function of radius, as you roughly know the distance to a particular void, you can do different methods. And yes, all of them show you a dip, and then you can look radially in that direction of the dip of the void. You can look radially and map the galaxies. So, you know, I want to show these methods have their merit. Now, this is something, you know, we all know, and you have great work done here on going from data to do cosmological parameters like omega m sigma 8. So this is done usually. You do a vector of correlation functions, and you write covariance metrics, and you use Bayes theorem. What this group in Zurich has done is actually, again, just simulations. You just throw simulations and simulations, and you know the machine will tell you what are the parameters, and then you show the one universe, and they claim that you get with, so this is just Planck, which is difficult to beat, but when they do it on kids, they claim with CNN, which is this purple line, you get better results than if you do just 2-point function. There's a lot in it. I have questions myself about it, reproducibility and so on. We can come to it later. And finally, if I got 2-3 minutes, is this okay? Yeah. I just want you to live with the idea that it's a beginning of a new era, despite my critical views on this, and it's far beyond just classifying objects. It's far beyond just cats and dogs, stars and galaxies. And you can really start bringing in simulations. You can think of any area you work on. If you do hydro simulations for galaxies or models for planet formation, you can really do that. So this is something we wanted to really understand it a bit better. And we looked at just the motion, another classic topic at the IoA, the motion of the Milky Way and Andromeda. And you know, there's a classic result from 1959, Volter and Kahn, called timing argument, which is just writing a very simple equation for the infall of two objects. And then others have elaborated on it, including Donlin and Bell. And this is a way of getting the mass. And we thought, oh, could we do something more fancy? Train simulations and pick up objects. So this is basically the result, what goes into the timing argument. Traditionally, it was just that. Some of us looked at the addition of lambda, which, by the way, makes a big difference to the mass you estimate if lambda is there or not there. And then you can see lots of papers on that, but we thought, let's take a fresh approach. And again, with Pablo Lemos and others, and this followed area work with Michael McLeod, we basically use Bayes theorem, the probability for parameters such as the mass given the observations, which are the infall velocity, also tangential velocity from Gaia and HST, given a model, and you have to do the probability for data given the parameters times the prior for the parameters divided by evidence and so on. And this shows you the difference in masses against the sample number. So, there's noise, but it comes quite right. So what the idea is with this likelihood-free inference is that you actually train on 2 million pairs, and you actually create that probability function, okay? You create it, you don't have to assume it's Gaussian. You create a function, you get form modeling. You put all the nasty effects of the observations into the model, and then you measure probability for data given parameters, and then you multiply by prior. And that's the answer. Unfortunately, with that method, we could only sorry. We could only measure the sum of the two. We can only measure the sum of the two, and it comes to be that number. Okay, so this is M31, M Milky Way, the sum, and this is measurement from literature of just the individual masses. What's interesting, actually, the timing argument does pretty well. If you do that, you get almost some answer, though how naive it is. So it also tells you, you learn something from the simulation, but you do learn because you can learn more about the scatter. You can see we still know rather poorly the mass of our own Milky Way. Okay. Now there's another paper that appeared recently from the collaboration called CAMELS, which I'm still trying to understand. They claim to use more parameters, and they claim they can actually isolate and tell the mass of each of them. So you can look at those papers, quite interesting. Okay, and last minute, I promise, is just to say that all that is, the work I showed was done with these students in that program, which we started 5 years ago with support from STFC, and Cambridge has its own program, and we look forward for extensions of that into the future. We got in 5 years 53 students, and it's nice it brought together people at UCL. I co-directed together with Nikos Konstantinis, who is a particle physicist, for example. We have 30 industry partners. So the students go to these companies and they learn all kinds of interesting techniques in AI, which they then bring back. So it's a 4-year program, as you know. 3.5 years, you have the core astronomy or particle physics, but they have half a year they spent with partners. So it's all, I think, we're quite pleased with it. The students seem to enjoy. These are the 5 students I had the privilege of supervising, and I showed some of their work earlier on. And I think there's a lot here for academia to learn from industry, vice versa, and also to prepare people for a dual career, because not everyone will end up as an academic by choice or not by choice. It's great to give people the face of those opportunities. And now we turn it with support of the UCL Provost into a center of data intensive science. And we have the CDT PhD program. We have an MSc program with about 70 students from all over the world. It's quite international. 400 applicants, by the way, could admit 70. And I know there are similar thoughts in other places in that direction. And we have the industry partners, an international angle, which is not only with kind of the usual institutions we collaborate with in the US, in the continent, but also we've initiated an activity with Jordan. Okay, so maybe data science could also help peace in the world. In some ways, it's universal language, maybe like music, if you want to get more spiritual and hopeful about this world. And it's quite nice, we got this support from the Newton Fund to run this program, which, by the way, on the Jordanian side has, our side, in terms of gender balance, about 20% female, and the Jordanian side is 60% female. Okay, so again, we open our eyes to the way things are done elsewhere. Maybe there are things we can learn. And they've been very interactive with us. We had an event at the British Embassy in Oman recently. Unfortunately, we could not actually have mutual visits in person. That's unfortunate because of COVID. But maybe we can continue that. So just to show you that this data science, beyond just solving problems in physical sciences, it could also has a merit of being very international, very broad. And this is my last slide, just to say that we're going through some industrial revolution here. Huge data sets in both spatial and time domain. And we have the challenges, I think, now to understand and explain and interpret, and also to scale up algorithms. So if something worked for you for a million, how do you know it's going to work for a billion? So there's data compression issues and so on. But it's also a great way of training PhD students and postdocs beyond academia and to establish international links. Thanks very much for listening.